Hello class, welcome to Stat 1200. I am your instructor William Yeoman, and today we are covering section 8.3, hypothesis tests for a population mean sigma, the standard deviation, unknown. The objectives for today are to test a hypothesis test about a mean using the p-value method, test a hypothesis about a mean using the critical value method. We begin this section with an example. Suppose that in a recent medical study, 76 subjects were placed on a low-fat diet. After 12 months, their sample mean weight loss was 2.2 kilograms, with a sample standard deviation of 6.1 kilograms. Can we conclude that the mean weight loss is greater than 0? If we knew the population standard deviation sigma, we would be able to compute the z-score of the sample mean to be z, which equals x bar minus mu over sigma divided by the square root of n, and use this test statistic to perform a hypothesis test. In this example, as it is usually the case, we do not know the population standard deviation. To proceed, we replace sigma with the sample standard deviation s and use the t statistic instead. So t is equal to x bar minus mu over the sample standard deviation s divided by the square root of n. When the null hypothesis is true, the t statistic has a student's t distribution with n minus 1 degrees of freedom. The assumptions for performing a hypothesis test for mu when the population standard deviation sigma is not known are as follows. We have a simple random sample, and that the sample size is large, greater than 30, or that the population standard deviation is approximately normal. Since we have a simple random sample, check on that assumption, and the sample size is large, check on the second assumption, we may proceed with the test. The issue is whether or not the mean weight loss mu is greater than 0. So our null hypothesis is mu equals 0, and our alternative hypothesis is mu is greater than 0. The test statistic t is equal to 2.2 minus 0 over 6.1 divided by the square root of 76, which is equal to 3.144. When the null hypothesis is true, the test statistic t has a student's t distribution with n minus 1, which is 76 minus 1, which equals 75 degrees of freedom. This is a right-tailed test, so the p-value is the area under the student's t-curve to the right of t, which we found to be 3.144. Using technology, we find the exact p-value to be equal to 0.0012. Since the p-value is less than 0.05, we reject the null hypothesis at the alpha equaling 0.05 level. Thus, here's the big important part of a hypothesis test, what our conclusion is. We conclude that the mean weight loss of people who adhere to this diet for 12 months is greater than 0. The p-value of the test statistic t is the probability, assuming the null hypothesis is true, of observing a value for the test statistic that disagrees as strongly as or more strongly with the null hypothesis than the value actually observed. The p-value is an area under the student's t-curve with n minus 1 degrees of freedom. The area is in the left tail, the right tail, or both tails, depending on the type of test. A left-tailed test. The p-value is the area to the left of t. A right-tailed test. The p-value is the area to the right of t. A two-tailed test. The p-value is the sum of the area to the left of the negative absolute value of t and to the right of the positive absolute value of t. When using a t-table, we cannot find the p-value exactly. Instead, we can only specify the p-value is between two values. In the last example, there are 75 degrees of freedom. We consult table A3 and find that the number 75 does not appear in the degrees of freedom column. We therefore use the next smallest, remember that, smallest number, which is 60. Now look across the row for the two numbers that bracket the observed value of 3.144. These are 2.915, so that's lower than 3.144, and 3.232 because that's higher than 3.144. So you can see how 3.114 is trapped in between those two numbers. The upper tail probabilities are 0.0025 for t equaling 2.915 and 0.001 for t equaling 3.232. The p-value must therefore be between 0.001 and 0.0025. We can conclude that the p-value is small enough to reject the null hypothesis at the alpha equals 0.05 level of significance. Since that whole range from 0.001 to 0.0025 is less than alpha, that's why we can reject it, because we know the p-value has to be somewhere in between those two numbers, and no matter where it is between those two numbers, it's still going to be less than 0.05. Suppose instead if we had the alternative hypothesis where that mu doesn't equal 0, the p-value would be the sum of the areas across the two tails. If using table A3, we can only specify that the p-value is between two values. We know that from table A3 that the area in one tail is between 0.001 and 0.0025. Therefore, the area between both tails, we now multiply it by 2, is 2 times 0.001, which equals 0.002, and 2 times 0.0025, which equals 0.005. Let's do an example. Example 1. Generic drugs are low-cost subsidies for brand name drugs. Before a generic drug can be sold in the United States, it must be tested and found to perform equivalently to the brand name product. The U.S. Food and Drug Administration is now supervising the testing of a new generic antifungal ointment. The brand name ointment is known to deliver a mean of 3.5 micrograms of the active ingredient to each square centimeter of skin. As part of the testing, 7 subjects apply the ointment. 6 hours later, the amount of drug that has been absorbed into the skin is measured. The amounts in micrograms are as follows: 2.6, 3.2, 2.1, 3.0, 3.1, 2.9, 3.7. How strong is the evidence that the mean amount absorbed differs from 3.5 micrograms? Use the alpha equals 0.01 level of significance. Because the sample is small, the population must be approximately normal. To check this, we're going to make a dot plot of the data. So if we look at the dot plot down here, the data seems pretty spread out, no big problems, no skewness, nothing is way too far away from anything else, so we don't see any outliers. So we can say it's reasonable to assume that this data is approximately normal and proceed. The null and alternative hypotheses are, so the null is that mu is equal to 3.5. And since we said differs, we don't care if it's larger or smaller, we just want to know if it's different. So that's going to be the alternative, which is mu is not equal to 3.5. We compute the sample mean and sample standard deviation from the sample. The value for the sample mean is 2.9429, and the sample standard deviation is 0.4995. The t-test statistic is 2.9429 minus 3.5 divided by 0.1888, which gives us negative 2.951. The number of degrees of freedom is the sample size minus 1, so 7 minus 1, which is 6. The alternative is a two-tailed test. So the p-value is the sum of the area to the left of the observed t-statistic of negative 2.951 and the area to the right of 2.951. Because remember, it's the area to the left of the negative absolute value and the area to the right of the positive absolute value. Using table A3, the two values that are closest to 2.951 in the row corresponding to 6 degrees of freedom are 2.447 and 3.143. The area to the right of 2.447 is 0.025, and the area to the right of 3.143 is 0.01. Therefore, the area of the right tail is between 0.01 and 0.025. So since we're doing two-tailed, we double those numbers, and we get that the p-value is between 0.02 and 0.05. And here's a graph below that kind of shows that. You can see the areas that were sandwiched in between and the shaded areas. The p-value is small enough to give us doubt about the truth of the null hypothesis. However, because the p-value is greater than 0.01, we do not reject the null hypothesis at the 0.01 level. So here's our big conclusion. There is not enough evidence to conclude that the mean amount of drug absorbed differs from 3.5 micrograms. The mean may be equal to 3.5 micrograms, we don't know, but we're just saying there's not enough evidence to say that it differs from that. What if we wanted to use the critical value method to test a hypothesis about a population mean when the standard deviation is unknown? We use the student's t-distribution. The critical values for the student's t-distribution can be found in table A3. So if we're doing a left-tailed test, the critical value is negative t alpha, which has an area of alpha to its left. Reject if t is less than or equal to negative t alpha. For our right-tailed test, the critical value is positive t alpha, which has an area of alpha to the right. So reject if the test statistic is greater than or equal to the critical value. Two-tailed. The critical values are t alpha by 2, which has an area of alpha by 2 to the right, and negative t alpha by 2, which has an area of alpha by 2 to its left. Reject if t is greater than or equal to t alpha by 2, or reject if the t statistic is less than the negative critical value, negative t alpha by 2. So now we're going to do an example using the critical value method. Example 2. A computer software vendor claims that a new version of their operating system will crash less than 6 times per year on average. A system administrator installs the operating system on a random sample of 41 computers. At the end of the year, the sample mean number of crashes is 7.1 with a standard deviation of 3.6. Can we conclude that the vendor's claim is false using the alpha equals 0.05 significance level? First, we check the assumptions. Do we have a simple random sample? Yes, we do. And is the sample size large enough? Yes, it is, so we don't have to check normality. The assumptions are satisfied. We have that the null hypothesis is mu equals 6, that's the claim, and the alternative hypothesis mu is greater than 6. We use a significance level of alpha equaling 0.05 and table A3. The number of degrees of freedom is the sample size minus 1, so 41 minus 1, which is 40. Since this is a right-tailed test, the critical value is the t-value with an area of 0.05 above it in the right tail. The critical value t alpha is, so we figure out where 40 and the area in the right tail of 0.05 come together, which in this box we see is 1.684. Just to remind you, we have that the sample mean is 7.1, our proposed population mean is 6, our sample standard deviation is 3.6, and our sample size was 41. The test statistic t is, we calculate as 7.1 minus 6 over 3.6 divided by the square root of 41, which gives us 1.957. Because this is our right-tailed test, we reject the null hypothesis if our test statistic is larger than or equal to our critical value. Since our test statistic was equal to 1.957 and our critical value was equal to 1.684, we see that our test statistic is larger than or equal to our critical value. Thus, we reject the null hypothesis. And because we rejected the null hypothesis, we can conclude that the mean number of crashes in a year is greater than 6.